This classical assumption says that the variance of the stochastic error has to be constant. And by constant, we mean that there's no systematic variation of that variance with one of the x's, for example. This, along with the assumption that the error terms are not correlated with one another, I think initially is often challenging for students to sort of imagine. So I'm going to try to give you a flavor for what this looks like and the circumstances in which it might arise, okay, or when we might violate it. Let me give you a little vocabulary first. If the variance is not constant, that is to say, if there is some variation in the variance of the stochastic error, as, for example, one of the x's varies, we say we have the condition called heteroskedasticity, okay? Homoskedasticity is what we have if we are in compliance with the classical assumption number 5, right? So homoskedasticity, we do not have a problem. Heteroskedasticity, we do have a problem. So what does this look like in? So here we have a typical y variable and a single explanatory variable, which we're calling z in this case. And we're imagining that this is a population regression line. So we have expected value of y given x, population regression line. And the evidence suggests that as the x's, or in this case the z's, rise, right, the band around the regression line that contains these data points, that band is getting bigger, right? Which means that the variation in the stochastic error, which is just the distance between any one of these data points and the line, okay, means the variance of the stochastic error is rising. So as the data points fan out, as the z variable rises, okay, we are looking at evidence that the variance in the stochastic error, epsilon, is actually getting bigger and bigger. All right. So what would some examples of this be? One that you're sort of familiar with already would be the house price and square footage problem. So if we had square feet here and we had house price here, okay, houses that have relatively large square footages attached to them could be really dumpy houses or in very bad neighborhoods, in which case their prices may be very low, or they could be in swanky neighborhoods, very nice neighborhoods, in which case their price could be very high, right? So the band of house prices for big houses could be quite significant depending upon location and house attributes, neighborhood attributes, and so on. On the other hand, if you have a very tiny house, okay, one that's way down here in the square footage spectrum, the chances of it having a super high price in a given community are pretty small, especially in a community like Greenville. So in this case, we think the variation in house prices around the mean, around the expected value of y given x here, or p given SQFT, the variation of those data points around that line is going to be much less. Okay, so that's one way in which you could see an increase in your z variable being associated with greater variation in the variance or standard deviation of the stochastic error. Okay, what would another example look like? We can clean that up a little bit. Okay, and another example could be taken from consumption and income. So this is kind of a classic example, consumption and income. So let's look at this one now. If we have income here and we have consumption up here, at very low levels of income, we're not going to see too much variation in consumption because you're basically consuming all of your income in order to survive. As your income grows and grows and grows and grows, however, we see more variation in consumption behavior. We have people who are the big savers, they're not consuming as much. We have the people who splurge a lot on consumption goods, they're consuming a lot more. And therefore we have a big variation or variance in the stochastic error. Again, stochastic error is just the distance of the data point from the population regression line. So if those are more spread out, we're going to get a bigger variance. Okay. There are other examples. Labor and output has been suggested as one. I won't talk too much about that right now, but I think you get the idea. Anytime that you have a variable that has a significant amount of variation in it, a huge amount of variation in it, for example, per capita income, or GDP, for example, just GDPs across countries. GDPs range from very small numbers to very, very large numbers. And if we see a big change in GDP across space, then whatever GDP is being used to explain on the y side of the variable is likely to give us this heteroskedasticity pattern. What we'll discover shortly is that if we violate this particular assumption, it makes it very difficult for us to accurately test hypotheses about these population parameters, beta 0 and beta 1, based on our estimates, beta 0 hat and beta 1 hat. So it's going to kind of mess up our hypothesis testing, but we'll have a technique for trying to fix that problem when it arises. I should mention also that this is a problem that cross-sectional data is noted for. So if you're ending up doing a cross-sectional study for your project, you're going to want to look to see whether you have this heteroskedasticity problem, and if you do, you'll want to try to correct it.